In this lecture, I am describing barium titanate structure. Barium titanate is ferroelectric, which also exhibit piezoelectricity. Let us first try to understand what is ferroelectric or what is piezoelectric or what is dielectric. What is the dielectric material? If you take the dielectric material and apply the electric field on it, then it polarizes. Okay, when you apply the electric field, polarization takes place. Polarization of charges takes place. And when this electric field is removed, okay, electric field removed, then this polarization vanishes. Such materials are called dielectric materials. If you take ferroelectric materials and apply electric field on it, then it polarizes. That is, polarization of charges takes place. And when this electric field removed, polarization remains. Remains as it is. Then that type of materials are called ferroelectric materials. Then let's go to see what is piezoelectric. Piezoelectric, like this barium titanate or quartz, these are the piezoelectric materials. If you take the piece of piezoelectric material and apply pressure along the mechanical axis. Let's say these two are the mechanical axis and we are applying the pressure. That is, we are compressing it. Then it is observed that charges are developed on the opposite surfaces. Let's say negative charge develop on top surface and positive charge develop on bottom surface. This is the case when we compress it. And the same material, if you elongate it, if you pull it away, if you elongate it, then again it is observed that charges develop on the opposite faces, but in this case, reverse manner. Now the positive will develop on the top and negative on the bottom. And this effect is called piezoelectric effect. Piezo means pressure. The pressure produces electric charges. That's why piezoelectric effect. Now the converse of this effect is also true. Converse of piezoelectric effect. Converse means instead of applying the pressure, we just apply the electric field. Now connect these two faces which are along the electrical axis of that material connect to the AC, alternating voltage. This is the cycle, AC cycle. In that half is positive and half cycle is negative. Now during the first half cycle, this surface gets a positive charge, this gets negative. So these two surfaces elongate as per this effect. When this is a positive and this is negative, that mechanical surfaces elongation takes place. And in the second half, this surface gets negative charge and this is getting positive charge. It means it compresses. So as per the frequency of the applied voltage, the material elongate and compress. That is converse piezoelectric effect. But here we are studying the structure of barium titanate, which is ferroelectric and also exhibit piezoelectricity. Piezoelectricity. Now this ferroelectric behavior of this material is observed below certain temperature. This is observed below certain temperature. That temperature is called Curie temperature. That temperature is Curie temperature. And for barium titanate, Curie temperature is 120 degrees Celsius. And so below 120 degree Celsius, it shows ferroelectric behavior. And above 120 degree, it shows a dielectric behavior. So below 120, ferroelectric. Above 120, dielectric. Why this happens? What changes takes place in the structure so the material transform from ferroelectric to dielectric or dielectric to ferroelectric? To understand that, let us draw the unit cell of barium titanate below 120 and above 120. So I am going to draw above 120. Above 120 degrees Celsius, it is observed that it has a cubic structure. This is the unit cell above 120 degree. And above 120, it is cubic. In this, I am going to show the atoms. Now there is barium atom, titanium, and oxygen. So here the barium ions occupy all the corner positions. So these are the barium ions. Barium ions. Then there is Oxygen. Oxygen ions occupy FC phase center position. So this is oxygen. This is the phase center of front surface, phase center of backside surface. And titanium ion is at the center. Titanium is at center. So you can see symmetry in this case. Symmetry. And when it is cubic, what happens? Positive ions coincide with center of positive ions coincide with center of negative ions and no net charge is present. So let me say that this is barium, then the red are oxygen, and this one is titanium. So at body center there is titanium. So in this diagram it means above 120 degree center of positive ions coincide with center of negative ions. So no net dipole is present. The charges neutralizes, and that is when material is dielectric. Now what happens when temperature changes to below 120 degree? Now here I will draw the unit cell for barium titanate below 120 degree Celsius. So what happens in this case? As temperature reduces below 120 degree Celsius, this oxygen and titanium move slightly from their natural position. Okay, they move slightly from their natural position. And the crystal elongated at along z direction. That means unit cell becomes tetragonal. It transforms from cubic to tetragonal. So let me draw the diagram for BaTiO3 above, sorry, below 120 degree. So unit cell is tetragonal in this case. This is the tetragonal, and let me show you barium ions at the eight corners, and Here is a titanium, and let me show the oxygens. Let's show by red color. So one is here, one is here. This is back side. This is the front side surface. Face center of this and face center of this. Let's see their symmetry. So this is what we get below 120 degree. That unit cell becomes tetragonal. And when this is the case, when the unit cell is tetragonal, center of positive and negative ions do not coincide. Positive and negative ions do not coincide. And so the dipole is generated. Dipole is produced along vertical direction. And that's why, this one is ferroelectric material. Dipoles are already present in this case. So that is the unit cell of barium titanate below and above 120 degree. And you can see here, this is tetragonal, this is cubic, and this is the top view. If you see the top view, there is a movement of charges and they are shifted and then they do not coincide. Now let us characterize the unit cell of this barium titanate. So let's see what is the atomic basis for this. Atomic basis is equals to 5 atoms per lattice point. And that 5 atoms are 1 barium, 1 barium, 3 oxygen, and 1 titanium. So total 5 atoms per lattice point. Then orientation of this atomic basis is this barium ion is at 0, 0, 0. Then titanium ion is at A by 2, A by 2, A by 2. And there are 3 oxygens. So first oxygen is at A by 2, A by 2, 0. Second oxygen is at A by 2, 0, A by 2. And the third oxygen is at 0, A by 2, A by 2. So this is the orientation of atomic basis. Then find out how many effective atoms per unit cell. We are going to find effective atoms per unit cell. Effective atoms Now barium is at the eight corners of the unit cell. See the unit cell? At the eight corners of the unit cell, barium ion is there. Barium ions are there. So its contribution is 1 by 8 into 8. That is equals to 1 barium ion. Then oxygen. Oxygen ions are at FCC position. The red one here in this case, they are at phase center position only. And so contribution of each phase center is half. Total there are six phases, so there are three. Three oxygen. And then titanium. Titanium is at the body center. So there is one titanium. So total 5 atoms per unit cell. Effective atoms 5 atoms per unit cell. And that is the titanium, barium titanium.